Okay, so we're on video 4. Sometimes, instead of the linearization itself and approximating, we're more interested in the change of f than we are in what f is. There might be an instance where we're concerned with the change of f, what's happening between 2 points, rather than the behavior at a given point on f. And so we can kind of use that same idea with linearization and approximation. If we think that f prime of a, from our definition, is the limit as x approaches a of f of x minus f of a over x minus a. And remember, we're approximating. And approximating insinuates error. So I'm accepting some level of error. Now, how much error determines on what we're using it for. I mean, error is relative. Sometimes a little bit of error. We use error in everyday measurements. If we are measuring how many gallons of paint, we use an approximation because we know as long as we're not off by an entire gallon, we're still going to need within a certain amount of paint, right? So unless it's a really finite, oh, I don't know if I should go with 3 gallons or 4, and we really want to be accurate so we can buy the right amount of paint, we don't end up with too much paint, within a certain amount of error, that's reasonable. But if we are launching rockets, let's say, we don't want to be off by a degree. We want to know exactly where we're launching it to. So error is relative. Error is acceptable and unacceptable depending on the circumstances. However, if we can assume some level of error, and that error can be controlled by how far apart x and a are really close, there's going to be less error. If x and a are far apart, there'll be more error. We can disregard that limit part for the purposes and then say, okay, we can approximate it through this, because this takes it from a tangent line to a secant line. And we're basically saying, okay, all tangent lines are secant lines where the distance between the 2 points is really, 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 really small. Well, if we call it really, 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 really small, but now we're not using approaching 0, now we're using this idea of, okay, it's close to 0, but it's not 0. If we can accept that with some level of error, we can change it from a tangent line to a secant line. And then we can say that f prime of a is approximately the change in f over the change in x. And if we do some basic algebraic rearranging, we can say that the change of f is approximately equal to f prime of a change in x. And this is the formula that we're going to use. So we can approximate the change in f using f prime of a. So let's put this in an example. We have f of x is equal to the square root of 1 plus x. Now we're given some additional information. We're given that we're centering it around 8. And we're specifically interested in how f is changing when x changes by 1. So not negative 1, but positive 1. How is f changing as I go from 8 to 9? That's what this means. Change of f is how f changes as I go from 8 to 9 if my change of x is 1. So we are going to go ahead and find what the change of f is using that formula. So we're going to estimate change in f using change of f equals f prime of a times x. So we're going to need f prime of x first, and then you're going to need to plug in a to find it. So pause if you want to do it on your own. I have this is 1 plus x to the 1/2, so it's 1/2 1 plus x to the negative 1/2. Chain rule would be just times 1, so there's no times 1 necessary for chain rule. So f prime at a is going to be 1/2 times 1 over the square root of 1 plus 8 is going to be 9, which is 1/6. That's my f prime of a. So then that's going to be 1/6. I forgot the change of x there. So 1/6 times 1, I come up with 1/6. Now remember, this is an estimation, estimation, estimation. So estimation is 0.16, excuse me. So that becomes my estimation. So now I'd like to see how off we are. How bad is our error? So remember, error is actual minus estimate, absolute value over actual. So now I'd like to know the actual difference between the change. Okay? So square root, the actual would be the square root of 10 minus minus 3, because this is f of 9 and this is f of 8. And the difference between those two is 0.162, according to my notes. So if I put that in, I get a difference of 0.025, or approximately 2.5%. So what does this give me? This gives me the knowledge, or this tells me that the change in f for this function right here, the change in f for this function, when I center it around 8 and go up by 1, the change of f is approximately 0.16666 for whatever. So then what I did is I said, okay, since I have a calculator present and I'm examining this skill, I'm both learning up an application and examining it for its worthiness so I can understand its pitfalls, I'm going to go ahead and examine the error as well. So the error in this case had to be found by finding what the change in f was, and here's where I found the actual change in f. And I found the actual change in f was 0.162, which is pretty close to 0.16666. I'm off. My error doesn't happen until I get to the 10th, 100th, thousandths place, so I have some pretty good validity there. And when I plug it into a percent error, it's 2.5%. It's a relatively small error for this change in f. Okay, so the next task is to estimate the difference between 16.5 to the 1/4 and 16 to the 1/4 using linear approximation and find error. So again, we have to decide, okay, we've got these two routes of linear approximation. We have the whole idea of finding the linear approximation, and then we have this idea of the change in f. And the change in f, let's go back to some algebra terms. When we talk about the change, we're talking about difference. Change, difference, we're looking about how is something at one point gone to a different point, and the way we quantify that change is how far they've traveled. So the fact that this is a subtraction problem is leading you to something interesting right there, because that tells you that this is a change in f problem instead of just a linear approximation straight up. So what I'm looking at is the change in f equals f prime at a times the change in x. Okay, so we need to figure out, we need to sleuth out. First of all, I need to know what f of x is. Second of all, I need to know what a is. And third of all, I need to know what the change of x is. Those are the three pieces I need to solve this problem. So see if you can figure out the parent kind of function, or the main function that's happening here. I'll give you a second. That's going to be x to the 1/4. Do you see that? That's what's happening here and here. And you're finding the difference between x to the 1/4 at two different points. So now we want to think about where we're centering at. And we're centering it around 16. We're starting at 16 and we're going up by 0.5. Now why did I not go 16.5 and down to 16 by 0.5? Why would I not use 16.5 negative 0.5? Because the function is here. And remember, the whole point of linear approximation is we're supposed to be making it easier, not harder. I can find the fourth root of 16. I cannot find the fourth root of 16.5. So it's much more reasonable to start at 16 and go up by 0.5 than the other way around. Although mathematically it could be done either way, but then you're missing the whole point of the linear approximation. So now I'm ready to go. F prime of x is equal to 1/4 x to the negative 3/4. So that f prime at 16 is 1/4 times 1 over, and the fourth root of x is 2. 2 times 2 is 4 times 2 is 8 times 2 is 16. So 2, but to the third it'd be 8. So I end up with 1 over 32, which matches my notes. And I also need to know what f, no, I don't need to know what f is, so never mind. Let me get rid of that. So now I'm ready with everything in my formula. The change of f is equal to f prime of a, which I have as 1 over 32. And I'm going to change 0.5 to 1/2, just so I can stay in fractions. And I end up with 1 over 64, which is approximately 0.015625, according to my notes. So, there you have it. That is my change in f estimation using this formula instead of flat out doing it. But now we need to find error. So to find error, actual minus estimate over actual. So I need the actual. So if you plug it into your calculator, I get the actual value here as 0.015445. So if you go actual or actual minus estimate over actual, I end up with a percent difference of about 1.2%, according to my notes. So fairly small difference, which suggests, and you can examine this on a graphing calculator, this suggests that the linearity between these 2 points is pretty good. The secant line is very close to what the tangent line is. These two x values are close enough to where the secant line and the tangent line are pretty darn equivalent. And that's the idea here. The secant line creating a linearization from the secant line is close enough to approximate a tangent line, which will approximate the linearization.